Hello, in this presentation, I'll be solving the problem of motion planning for multiple autonomous vehicles using a modified form of the general artificial potential field method, and later on we'll extend the solution framework to an algorithm known as elastic strip. The introduction to the problem in general is a separate video. The link should be somewhere in the video description. So, artificial potential fields method in general are very widely used, and there's a very good reason for that, because they are reactive planning methods. They instantaneously see the scenario, measure some distances, and extremely fast compute the next move. And as we know, in all such methods, there is always a great problem. That means the algorithm is neither complete nor optimal. So in a general robotic scenario like this, where this is my source and this is some obstacle out here, there are some obstacle out here, the robot can decide to move like this in pursuit of this goal and end up having no way to go, completely stuck. So they are neither complete nor they are optimal. It can take way bad parts like this. They are not globally optimal, although they are locally optimal. So artificial potential field in general, for let me talk in respect of a mobile robot scenario first. If this is my source or the current robot position and this is my goal, and correspondingly I have got some obstacles, say an obstacle like this, an obstacle like this, and any general obstacle like this. All these obstacles repel the robot. All these obstacles do not allow the robot to come here. So this obstacle, it will repel the robot like this. This obstacle is very far, so the repulsion will be very small. It's inversely proportional to this square of distance or nth power of distance. So they die off very fast. And similarly, this obstacle out here, it's very far off, so it will repel very small, and the goal will attract the robot. So the goal will attract the robot like this. And in general, what we'll see is that the robot will start taking towards this path. And let me take into some interesting scenario. The goal keeps attracting the robot, say until when it reaches the point out here. Now when it reaches this point out here, the robot is very close to this obstacle, so it sends a very strong repulsion force. It is not that strong out here. It sends a small repulsion force. It's not at all, so it will be very small repulsion force out here, and the goal attracts. The goal attracts using some force like this. So the overall motion will be the vector addition of all these, which means that the initial direction in which will be the vector addition of all this, which means the direction in which the robot would be traveling will be like this over here, and that is how the robot will basically move. Over here, when it reaches, it travels like this again here, attracted by the goal and repelled by the obstacles. Here, this as it reaches somewhere out here, the repulsion from this obstacle will get very high, and as a result it will go somewhere like this. When the repulsion from this obstacle gets very high, it will immediately take in a opposite turn. It will come like this. Now all the obstacles are very far away and it can nicely travel towards this goal. So that's how the artificial potential fields method function. Of course, in general, when we apply these methods, in practice, when we apply these method at any general point, say out over here, we sample the distances to only some points. So let me say I sample out the distances to 8 points. So these are 1, 2, 3, 4, 5, 6 and 7 and 8. So these are the only points that the robot would be seeing at. It will not see at in any other direction. These are the only 8 directions that the robot will see at, and of course it will always see the goal. It will be always attracted to the goal. So we sample out the direction to 8 points, or sometimes bigger ring is available to more number of points, and those are the only points in which the robot sees in its pursuit of the goal. So that was a very brief introduction to the artificial potential field in general, and that we know that these methods cause a lot of problem. And why do they cause a lot of problem? The first is when I have a very narrow structure like this and I start my journey here, my goal is somewhere around here. This wall will send a strong repulsion force. It will come here. This now this wall starts sending a strong repulsion force. Now there's no force, but it's going by momentum. This wall will now send a strong repulsion force, and the robot will oscillate in such kinds of structures. So oscillation in narrow corridor-like scenarios is the first problem that is associated with them. If I directly apply to a road scenario, which is what I try to do like this, I took a road-like scenario, and I say there are two vehicles, a vehicle behind which is traveling at fast speed and a vehicle slow which is traveling at the slow speed ahead. What will happen is that this vehicle will be attracted by the goal as in this vehicle, and because of this vehicle will be repelled behind. So that's all that is happening. While what should be happening is that this vehicle should have overtaken this vehicle and this vehicle should have dipped, cooperating along for this vehicle. So there's nothing like overtaking that can take place in its normal philosophy. As well as if there is an obstacle like this, now this is a zero potential area. And why is it a zero potential area? The repulsion from this wall cancels the repulsion from this wall. This obstacle repels backward and the goal attracts forward, so all the forces carry out each other. And like this, if we generalize the scenario, there are many zero potential areas, which is another limitation of the lateral potentials. And as we see that even if a vehicle is here and the second vehicle somehow by some magic is overtaking this vehicle will repel this vehicle at a force like this. So even though it's trying to turn, even though it's trying to dipping, but because the projection of this force in this lateral side is very small, so the cooperation is very weak. What we want is a nice little dip out here. What it's doing is that it's dipping really slowly. So in general, the artificial potential fields cannot be modeled for road-like scenarios like this, and we need to do something to enable them work in road-like scenarios like this, which is why we don't call the method artificial potential field, but we call it as lateral potentials. Now overall, whenever I plan my vehicle, there are always two things that I need to do. One is planning what my lateral position would be, and which is normally done by steering. By steering, I decide whether I need to drive here or here, and the other is more of a speed control, where I decide with what speed do I need to drive. So they are two completely separate but related planning aspects. One is the steering control, the other is the speed control. I'll first be looking at the lateral planning, wherein the concept of lateral potential would be used, which is the main crux of this presentation. I'll then be looking as my problem 2, the problem of speed control, and that's the most important slide of the presentation. Now consider a scenario like this, and I need to use some algorithm which is in some way similar to the concept of artificial potential field. So the first thing I know that I cannot compute using all the interesting things in this environment. I will have to sample out my distance measures in some direction. I cannot measure potential source from everything that would be here. There would be some obstacle out here, there would be some obstacle out here, there would be some vehicle out here. I cannot measure from everywhere, so I need to sample out points. So these are 1, 2, 3, 4, 5 and 6 points that I had, 6 directions that I have sampled out. What each sample says, like I take the example of the first one or the forward one, I'll measure the forward distance across all these points out here. So I'll measure this distance, I'll measure this distance, I'll measure this distance, I'll measure this distance, and I'll simply take the minimum of them, which is this. So that was the case for my forward direction, and similarly for the other directions. I'll take the minimum of the entire points that lie in the entire corner or the entire line segment that you see out here. Now, since I have said that I will be only taking potential from 6 of these, or the only source of repulsion would be these 6 obstacles that I have taken out here, or obstacles in the 6 direction that I have taken out here. Next, as my design methodology, I say let me take each and every obstacle separately. So I'll first study this thing. I'll say only imagine that there was a vehicle out here, and imagine there was a blue vehicle out here. Do not imagine the road boundaries, do not imagine the other vehicles, do not imagine anything else, and simply decide what would you have done. And when I say what would you have done, I mean two questions. Firstly, would you have steered left or right? That is one thing that you need to decide. And second thing that you need to decide is by what magnitude would you have steered. So the first question is steering left or right, and the other is steering in by which magnitude. Now, for the first question, for this very particular example where I'm only considering the forward direction, I say that steering clockwise or anti-clockwise, or steering left to right, is what I call as an obstacle avoidance strategy or vehicle avoidance strategy, and I'll be talking about it in the next slide. So there's some strategy which gives me this magical sign, or this magical direction. The second is the magnitude, and I say my time to collision will be will denote the magnitude. So let us say this was traveling with speed v1, this was traveling with speed v2. My time to collision, if any, would be v1 minus v2. It'll basically be this distance d divided by v1 minus v2. So that is my time to collision. If this is a static obstacle, then of course v1 gets 0. In fact, it will be v2 minus v1. So v1 gets 0, so that will be d by v. And why did I take time to collision and not distance as a measure? It's because if this vehicle is traveling very slowly, but it's traveling in the forward direction, then I can nicely take a steering like this. But on the other hand, if it was a static obstacle, I'll have to turn immediately. If this is a fast moving vehicle, then I can be more comfortable, because I know by the time I reach here, it would have reached somewhere out here. And of course, if this vehicle is moving faster than this vehicle, my time to collision will be infinity. Basically, the two will never collide. So I need not turn anything. I need not even consider anything. I can simply go forward. So this was the first case for the forward direction. I've taken time to collision as my magnitude of steering. If time to collision is very small, my steering would be very high. If time to collision is very high, my steering would be very small. The second that I take is this side. So imagine you are the vehicle out here. After this distance, there's some obstacle. We do not know what it is, but there is some obstacle. And obviously, I need not discuss the direction. You'll obviously turn right. And you'll turn right by a factor inversely proportional to the distance. More the distance, the less you turn. The less the distance you need, so if you are somewhere like this, you need to take very sharp turn. It's completely the opposite for this. And let me take this case. You are the vehicle out here. After this, there is some obstacle. I still do not know what it is. There is some obstacle over here. So you obviously take the counterclockwise turn, or you take the left turn by something that is proportional, again inversely proportional to the distance. If distance is very less, then you turn very much. If the distance is very much, you turn very less. And this case would be opposite. So in fact, what this diagonal source of potential or the diagonal source of repulsion would be doing, it will be acting as a forerunner for my side potential. It will basically inform me in advance in what obstacles are coming, whether the distance is about to get very small in the future, so that I can take preventive steps well in advance. And if I don't take it, the same obstacle will soon be seen by the side potential, and I'll have to take the action there. So if there's an obstacle out here and I'm the vehicle out here, I see something from the diagonal, I turn well in advance. If I cannot, I will soon be found in a scenario like this where I will have to take a turn. And what my back potential does is only and only cooperation. Now, I know that in driving, we never look behind, we never care of what lies behind us, except for only one situation, wherein that situation there is a vehicle which is trying to, this is the green vehicle and this is the pink vehicle, it's trying to overtake us, in which case we overtake in the opposite direction. So again, I need to decide the magnitude and I need to decide the sign. The sign would be given by vehicle avoidance strategy. If this turns right, I'll turn left. If this turns left, I'll turn right. So it'll basically be the converse of vehicle avoidance strategy of this vehicle, and the time to collision will give me the magnitude. If time to collision is very low, I need to turn very high. So basically we've seen that they were always two things, direction and the magnitude, except for these two cases. The direction was pretty obvious and the distance measure was used, and for both these, the front and the back, the direction was not obvious and the time to collision was used as a measure in place of the distance. And I promised I would say that how the vehicle avoidance strategy or the direction to steer in case of obstacle ahead and the vehicle avoidance strategy or the direction to overtake with a vehicle ahead would be decided. So the obstacle avoidance strategy I will deal first. If suppose I am a vehicle here and I have, with my forward potential or my forward repulsion, I have sensed an obstacle lying out here. If this obstacle is more towards the left of the road, I'll go right. And if this obstacle is more on the right of the, it's more on the right of the road, I'll go left. So assumption is a narrow kind of road. I basically need some quick and dirty method to decide this. I cannot invest bulk of computation. It's a reactive planning method. I need some quick and dirty heuristic. It may hold, it may not hold. But as it looks in from practically what we see in experimental scenario, this heuristic would hold. It'll at least give us a way to avoid the obstacle. And the other is vehicle avoidance strategy, where I see the same scenario, but in place of obstacle there is a vehicle which lies in front. If I'm exactly behind, then I will follow overtake from the right strategy. I'll turn overtake, and the converse strategy would be used for this. It'll dip leftward for cooperation. If I am more on the right and this is more on the left, so I'll overtake from the right and this will dip leftward. And if the converse happens, I am more on the right and this is more on the left, I'll overtake from the left. And this will overtake from the right. I'll have to draw these larger enough so that they are ahead and behind of each other by some magnitude, which is now. So if I'm more on the left, then I'll overtake from the left. And this will overtake from the right, which is different from natural driving scenarios where we always say always overtake from the right. But in an unorganized or chaotic traffic, if you see that overtaking from the left is clearly better, you can always overtake from the left. So that's how my two strategy parameters would be decided. This one's for the forward potential, and this one's for the back potential, where this is the forward potential and this one is the back potential. And one Once I have solved the problem separately for each of these potential, I simply take a weighted addition of all the potential sources. So I simply add all these potential sources. Now the problem is that different potential sources, some use time to collision, some use any other thing. The diagonal distances would always be much larger than the side distances, so they are in different domains, and whenever I add things in different domains, I simply weight them up. So they are simply combined in by different weights, and the magic number that I basically get from there is my desired orientation with respect to the road. So if I know that my potential is a lot rightward, it's a very large positive potential, that probably means I was somewhere very close to the road, and if I was very close to the road, that means somewhere my orientation should have been like this, so that this distance could be enlarged. So I make my steering effort in such a way that I get this desired orientation, and if my steering velocity is restricted, if my steering velocity is bound to be some value, so it's less than omega max, then I make the maximum possible effort that I can do in order to get this orientation. And basically, when we implement when we add and implement this up, what happens when when the vehicle goes very near the left boundary, it steers and gets away. When it gets very close to the obstacle, it steers and gets away. When it sees nice to little obstacle, it sees this obstacle, gets away. It sees and it sees this obstacle and finally gets away. So it can navigate across very easily across all these scenarios. But so far I have only played with the steering and I have not played with speed. Now speed, even in this kind of scenarios, it plays a very important role. If you leave your vehicle at very high constant speed and you say that there is an obstacle out here, there is an obstacle out here, you have got a very high speed, it'll go zoo, it'll try to avoid this obstacle, and it'll either bump out over here, or it'll automatically try to avoid this obstacle and it'll bump out over here. So the problem was that I had to reduce my speed out here. On the other hand, if I take very small speed, what will happen out here is that I will go very slowly and slowly and slowly and slowly and slowly. So this is bad because I take a lot of time, and this is bad because there is a lot of speed. So I need to adjust my speed accordingly, and the speed principle is very simple. At any time, see where is the nearest obstacle ahead, which I was already computing, and this distance can be converted into what is the maximum possible speed that I have. Basically the factor that we have used is that my maximum possible speed that I can display will be root d square by 2 times a factor called as aggression times a factor called as acceleration, which means if I take an unaggressive braking, then I will not collide. So by this very simple factor, I can set my speed. I simply see what is the distance, what are the safety distances to be kept, and what is the braking, and what's the maximum speed that I can display at that particular time. And I always display the maximum I always display the maximum speed at that time. We subtracted the safety distance from here. The only problem that this methodology has is that sometimes the vehicle is in scenarios like this. So I not only, it's basically oriented in this direction, so I not only measure this distance in the forward direction, I also measure distances in the heading direction of the vehicle, and the minimum of 2 is being taken. This is a distance which was not being measured previously, so it's a new distance I'll have to measure. And accordingly, at every time, I'll set the maximum possible speed such that it does not collide. Now remember, the problem with a high speed was only that it was colliding, it was bumping. If I can stop that, I can make the vehicle nicely navigate this, and that's what I have done. And if I am adding potentials from different sources by different weights, those weights out here will be my parameters. Now what these parameters do, there is one parameter which says that if there is an obstacle, if the how scared are you from the obstacle. So if you're very scared, you'll immediately turn and then travel straight. If you're not at all scared, you will travel like this and then you will take a sharp turn and then again go straight, and there's something in between. So that's lateral sensitivity. There's another factor which says how scared are you from the anything that is at your side. So let's say road boundaries at the side. So when you start here, you'll immediately go here, you'll overshoot, you'll basically oscillate a little bit, and you'll nicely end up in the middle. If you're not at all scared, you will travel almost straight. If you're a little scared, you will go somewhere in the center. Mixed sensitivity is a mixture of both these lateral and longitudinal sensitivities. And cooperation means that if there's a vehicle behind, how much will you dip? Whether will you dip too much and then travel straight, or you'll not at all dip, or you'll dip just little or a little larger. So these are all factors which are parameters in my algorithm that I need to optimize or that I need to manually set. And based on this is what the results that we have obtained. This is an overtake along with obstacle avoidance. This one is a dual overtake. It overtakes both these vehicles out here. And this is another for kind of dual overtake. It overtakes both these vehicles out here. This one was overtaken from the right and this one from the left, so it did not try to do anything fancy. It simply went straight ahead. And as I said, if you're too scared of the obstacle, you will you will travel like this. If you're not at all scared, you will travel like this, and this is how the length of gets affected. This again, if you're too scared of the if you're too cooperative, you will dip too much, and if you're too less cooperative, you'll basically travel straight. You'll give no sense to the other vehicle who will now have to overtake using a very steep trajectory. So that's what happens to the more cooperation means the path of this vehicle gets bad and this vehicle and the vehicle actually overtaking gets good. A very high cooperation or the later regions means there's a large difference in their paths. This vehicle is cooperating too much and therefore it has a very bad path length, and obviously this has a very good path length. It does not have to do anything, it just needs to drive straight. And that's what happens with the road boundaries. If you apply too much force out here, then that is what you'll do. And if you do not apply any force, you'll basically travel straight. Okay, so that was more or less the entire algorithm. It seems that it works well for all scenarios. In fact, it does for all the scenarios that we experimented out with. Now we'll try to make that algorithm better, and in order to make this better, I'll have to introduce one term that is known as an elastic strip. Now, this is what is a trajectory of a mobile robot being followed. A mobile robot is actually following this trajectory. Say it is somewhere out here. As these obstacles move, let's say this obstacles move out here, this obstacle moves out here, it is now like this. They will repel the trajectory, and as a result, it will get elongated both like this and like this. So as these obstacles move, there's an elastic strip, and we all know what is the property of elastic strip. If you apply force to the strip in this direction, which this obstacle by its very nature is applying, in fact, it's applying a virtual force like this. All the obstacles we know they repel in potential methods. So this obstacle is applying forces like this, and this obstacle is applying forces like this, and because of which this elastic strip is getting repelled. As they continue to move on, the forces will get modified and they'll get more and more repelled. And there's another force which tries to hold on the elastic strip. And as we know that in any elastic strip, if you entangle it, if you deform it into this shape, it will automatically come into this shape. The elastic strip or a rubber band or a spring for that nature, it tries to retain its original shape. So that is what is stopping these forces to push it up very hard. The internal force of the spring or the internal force of the elastic strip or this property, it is holding up the strip from going too far under the influence of these forces, and therefore very far into the future, if my robot is out here and these are the two obstacles out here and this is the third one, that is what the path would be. So that that's a very simple property of the elastic strip that we have, and we'll be using this in our algorithm framework, where this would be called as the trajectory being followed. So what are the problems associated with the lateral potential or the artificial potential field method that we need to solve? These are the two normal problems. They are neither optimal nor they are complete. So we need to do something about it. We need to make them near optimal and near complete, if not optimal and complete. The other problem that happened in the previous method that I presented, that I introduced some strategy variables. I introduced in two strategy variables, which was about obstacle avoidance and vehicle avoidance. And we placed in some quick and dirty heuristic. We said that this is a quick and dirty method of fixing this, and this should always work. It may or may not always work, which was the problem of lack of completeness and lack of optimality. Here we'll be taking in a more better approach, where we'll say that we'll try in all combinations. I mean, each one of these could be either clockwise or anti-clockwise. So we'll say we'll try all combination of methods. We'll try overtaking every obstacle from the right and left and every combination of them, and similarly for the vehicles, and we'll select the best plan. So these are the three problems. We'll be solving all these three of them in this method, or the method of elastic strip. Now, before I even hint you regarding what the method is, before I even present you little basics of this new method, there are some things that we'd like to get it straight. Now, whenever any algorithm, it has to choose between multiple possible plans, the very first thing we need to do is to formulate an objective function. We need to in fact do it even before we write down the algorithm, or even before we write down the code for it. So here, as it would be clear from the previous slide, I would be working out with multiple plans. I'll need to decide which one is good, which one is bad. So we will need some objective function which takes in a trajectory as an input and generates it, which basically takes in two trajectories as inputs and tells me tau 1 is better, tau 2 is better, or which of these two plans is better. Now, ideally, this function is very simple to design, except for this problem, wherein we would be dealing with not the complete trajectories, but we would be dealing with partial trajectories. So I'll say this is the segment of the road, there are some obstacles like this, and there's some vehicle like this. I'll not have to plan my trajectory till the very end. I'll try to plan till whatever point I can. So let's say I can overcome these two, but I currently do not know how to overcome this vehicle. So I'll say, okay, this is my valid trajectory. I'll say that maybe I know how to overcome this obstacle, I do not know how to overcome this vehicle. This is a valid trajectory. Out of these two, this one is better because it makes me travel more longitudinally, and as we know, there's a better chance of completeness from this trajectory as compared to this trajectory, because this might have been a static obstacle trying to trap the vehicle in some way. So the more we go ahead, the better is the trajectory, because the more chances are that the plan would be complete. And that's my first point. Apart from this, the other points are what you would normally expect. In a road scenario, I've always said that maximizing lateral clearance is always much better than minimizing time. And why do I need to consider time at all? Because sometimes my trajectory that maximizes lateral clearance can be very odd. So after this is a high priority and this is a little low priority. And we know that with number 1 and number 2, the only problem is that they don't cater to any kind of cooperation. So a vehicle here and a vehicle here, this vehicle has no incentive of dipping here so that the overtake of this vehicle can be comfortable. So I add in number 3 to give some incentive to cooperating. They are in non-strict order. That means they don't have a strict 1 to 3 relationship. Now, the little problem with all these 4 objectives that I have stated out so far is that suppose I am here, my other vehicle is out here, and somehow I cannot decide whether to overtake it from left or right because there's something that's causing infeasibility. Let's say the two vehicles are very close to each other, so I don't have enough separation to overtake, and therefore I cannot decide between left and right. And by these four objectives, it looks that they'll travel more or less equally longitudinally. They'll again have almost the same lateral clearance. This one will have a little lesser time, but they are almost the same time. I'm thinking non-strictly. For an overtaking vehicle, there is obviously no cooperation. So for such kind of tie breaking, I use the general principle that whatever heuristic was valid in my lateral potentials, that will be given a higher priority here. So that means because this vehicle is more on the right, this will be given a higher priority as compared to this vehicle. So that's an additional constraint that I have added for tie breaking. Whenever two plans seem to be doing equally well, the one that does it by the application of the lateral potential vehicle avoidance and obstacle avoidance heuristic is always better. So I have decided in some kind of objective function. I have, based on whatever was my understanding of the problem, I have said that there is some kind of objective function that I can use to compare plans. The second thing that I always need to do is to the second thing that I always need to do even before I comment upon the algorithm, before I present the algorithm, before I code the algorithm, is to have a feasibility criterion, what gets feasible and what is not feasible. In general, it's very simple. If this is my vehicle here, these are the obstacle, there's some vehicle out here, this trajectory would be called as feasible. It does not collide with any obstacle, it does not collide with any other vehicle, and anything like this would be called as infeasible because it collides with or with some obstacle. For planning purposes, I can say, let us assume that for feasibility analysis, that this vehicle was traveling at a constant speed, so that I can judge whether these two vehicles collide or they do not collide. The problem is that here I'm not dealing with complete plans, as I said, that make the vehicle go right towards the end till the goal. I'm dealing with partial plans. So I may have to say that you are a vehicle here, there's some obstacle out here, there's some vehicle out here, you try to go like this, but there is another vehicle out here, so you will have to stop here. I may have to ask the vehicle to stop here. I cannot reach the road segment end, and if I do so and my vehicle is out here, suppose this was traveling at a very small speed of 3 miles per hour and this was traveling at very good speed of 30 miles per hour, they both will collide. So I need to ensure at any point I have enough distance that this vehicle is able to slow down. It's able to slow down and not cause this vehicle. So at any point, in fact, I may have to stop my plan somewhere near here into the future. I might say that this does not look nice. Now you'll have to stop here. So at every point, the vehicle should have enough speed that it can stop without collision if it can do nothing better. So no collision from the vehicle in front, even if you are asked to stop, or even if you are asked to terminate your plan at any general time. And similarly, let us say this was a very was a very slow moving vehicle here. There was a very fast moving vehicle here. So let's say this time this was traveling at 10 miles per hour. This was traveling at 30 miles per hour. It saw an obstacle out here. It decided this nice little strategy. And it said that even if this vehicle is moving at 30 miles per hour, it will be okay. I can move. But now what happened is that because of some reason, I had to stop my vehicle here. Now, do I have enough time? And at that time, this vehicle would have been somewhere here. Now, do I have enough time? Or let us say, does this vehicle have enough time to slow down from 30 miles per hour to at least 10 miles per hour to stop collision as per this distance? If no, then this is infeasible. This would not be called as infeasible, because again I may have to short my plan and I may have to ask my vehicle to terminate my plan over here. So do I have enough time for this? What in general we observe is that if I am moving out here, I never make a lane change if there is a very fast moving vehicle out here. I know that this vehicle will not be able to slow down. So before making any lane change, we make sure there is no fast moving vehicle that is very near behind. And that's what was the problem with this scenario. The 10 miles vehicle did plan to overtake the obstacle, did plan to overtake did think that it will not collide with this vehicle, but because it had to terminate its plan, suddenly a collision happened. So I'll check that I should have enough time in my planning scenario. In any scenario, I should have enough time to stop if this vehicle to stop sufficiently catering to the needs of this vehicle. So if there is a slow moving vehicle here and I'm a fast moving vehicle and this is the scenario somewhere in the future, I should have enough time to stop considering distance d1, and the vehicle behind me, suppose it's traveling at a higher speed than me, it should have enough time to stop as per distance d2. These are the two additional constraints, because I'm making partial plans, because I'm not making complete plans. And with this, the algorithm effectively starts. Uh, so whenever I introduce an algorithm, I introduce some terminologies along with it. And for this algorithm, I'll basically use a very standard terminology of a trajectory, which is simply the trajectory by which the vehicle is planning, so there's no strings attached to it. However, I will always be careful of something like this. If there is a static obstacle out here, I can never come into this scenario. This scenario was completely acceptable if this was a moving vehicle and I was a moving vehicle. Even if this vehicle was traveling very slow, I would have traveled at some speed and maybe at a later stage when scenarios get preferable overtaken it. But now with this scenario, I'll have to basically wait till eternity, because this obstacle will not move. Unless somebody comes and picks this obstacle up, it will not move. So I will be very scared of this scenario in this entire presentation. I'll stop it from happening. I'll sense it well in advance. I will see to it that I do not fall into this kind of scenario, because in this scenario I can neither take right nor I can take left. I'm basically stuck. I'm too close to the obstacle. So in order to sense this scenario well in advance, in order to take preventive steps well in advance, apart from maintaining a trajectory, I may sometimes maintain another trajectory. So let's say this was my tau and I'll maintain another trajectory which follows the same principle as this trajectory, which is computed by all the varied techniques and tools that I would be presenting later on as this trajectory, with an additional constraint that I only consider static obstacles. I do not consider any other vehicles. So my normal trajectory is the trajectory computed considering everything, moving vehicles, obstacles, everything. My obstacle only trajectory is the trajectory which is constructed only considering to the static obstacle, no other vehicle. So if I have a scenario like this, there are some vehicles out here and there are some static obstacles out here. I'll take two snapshots of this. This snapshot I will use for computing my normal trajectory, and I'll simply rub the moving vehicles. I'll get a simplified scenario that I'll be using for computing the obstacle only trajectory. And the third is strategy. As I said, that we had strategy parameters in the lateral potential, which was vehicle avoidance strategy and obstacle avoidance strategy. We tried all combinations or permutations of each one of these, and we computed the best trajectory, which is this. I need to store which strategies were actually used for which represent this trajectory tau. So the strategy is only a parameter which is storing the vehicle avoidance and the obstacle avoidance strategies of the lateral potentials. So these are the three very related terminologies that I have. And with this, we actually start discussion on the algorithm. So it is a planning and a path. It's a path planning, path correcting, path rectifying algorithm. And what do these algorithm does is that my planner keeps a very close look at what's happening in the road scenario. If there are new obstacle, it basically sees the scenario and this is my vehicle being followed. My planner continuously sees the environment, and whenever there occurs any change, suppose this was the old trajectory, any change occur, there happen to be an obstacle like this, it will immediately rectify the plan. So that's what my planner is doing. It's immediate, it's at all times it is seeing what's happening. A new obstacle, it rectifies the plan. An obstacle went away, it rectifies the plan. It's rectifying the plan as the environment changes. The vehicle moves, now it's at position here, it modifies the start point to this, and correspondingly the trajectory gets modified. The vehicle slipped, it forms this trajectory. So my planner is continuously looking at the environment and it's making the plans. There is a control algorithm which is physically moving the vehicle, which is physically giving controls to the vehicle, which is physically operating the steering and the wheel. So there is a control algorithm. At every time it asks the planner, give me the best trajectory that you have, and the planner replies with an answer. It says this is the best trajectory as per what I'm currently seeing. So there's a separate planning algorithm and a separate controlling algorithm. The planner is continuously rectifying the plan, it's continuously working on the plan. And of course, when I'll control, what will happen is that my position will change, the vehicle will be here, and that the planner will see, it will continue, it will immediately rectify. So what we have as the general framework out here is, now planning problem is, in general, as we know, there is a speed component to it and there is a path component to it, and in general the two components are very correlated to each other. An ideal trajectory plan would be where in some regions the vehicle travels very fast, then slows down, travels very fast, then again does something, slows down, there may be obstacles out here, and so on. There may be vehicles depending upon which it has to accelerate or slow down. So I need to simultaneously work over speed and path, and we know that from an optimization perspective that's impossible to do. That's a very computationally expensive task. My path depends on my speed depends on my path. If I work on both simultaneously, it becomes a very difficult planning problem. It becomes a very difficult problem to deal with. So I simply divide these two problems. I'll say let us take speed separate and let us say path separate. Let me first fix the speed, and for this speed I'll calculate the path. Now that is what this algorithm will first do. It will try to fix the speed. And how will it fix the speed? Now there's one thing very exciting because of which we can vertically divide this problem, and what that thing exciting is, suppose there's a nice obstacle framework out here. What a normal driver would do, he'll drive very fast, he'll slow down in this region, he'll again come here, he'll slow down very much because it's a complex obstacle framework, he'll slow down and then he'll accelerate. So what's happening is, at every time I'm trying to find the maximum speed that I can drive as per what I'm currently seeing. Here I saw the obstacle was very far away, I was driving fast. Here I saw the obstacle are very close, I'm driving slow. Here I see the obstacles are very far away, I'm driving fast. And the same thing is in case of the moving vehicles. So at every time how human drivers drive, they see the scenario, they see how far the obstacle or the other vehicles are, and correspondingly decide they drive. So at any time, I'll go back, at any time my planner will see how far the nearest obstacle is, how far the obstacles in general are, and it will immediately set a constant speed which will be used throughout for the planning. So that means at this time, what my planner would have seen is very far obstacles. This run distance is very large. Let's keep the vehicle very, let's keep the speed very large, while if the vehicle did not actually follow this trajectory very neatly, if it came in something like this, it would have said, oh my god, very close obstacle, reduce its speed. So it would have said that now your speed will be very slow until you overcome this obstacle. And here it would have said no obstacle ahead, you can be very fast. So that's the first thing that I'll be doing. I'll split the problem of planning vertically into problem of speed planning. For the problem of speed planning, I simply said that see the immediate scenario and decide the best speed. And for this speed, I would be doing the rest of the planning. And how the rest of the planning is done, my planner already has in some plan like this. So this was the plan that I previously presented. So it already has a plan like this. Let me not draw the obstacles, let me not draw any other vehicles, let me only draw the road boundary, the vehicle out here, and the plan like this. Now suddenly a new obstacle may have come here. The vehicle here may have changed its speed, it may have started accelerating, it may have come to which may make the plan infeasible here, or this vehicle itself is continuously changing its speed, so now it might have increased its speed. Increasing speed means that all the infeasibility criterion will change. That means that now after this point, the vehicle is very close to this vehicle, and therefore it cannot, under the modified speed, occupy this position. So my plan gets infeasible here. So I'll identify the nearest point where my plan is infeasible. I identify the first point as per the change scenario, whatever my algorithm is seeing. I identify the first point where my plan is infeasible. And because the plan is infeasible, basically if it was infeasible here, then all this does not matter. The vehicle will never be able to enjoy this position. If it enjoys this position, it will soon end up in a collision. So I'll simply take a scissor and I will cut this plan. I'll take a scissor and I'll cut this plan. It's all useless for me now. It's infeasible. So at any time, my planner will only retain the feasible part of the plan. Now once it retains only the feasible part of the plan, there is again something that could have happened. Now initially my plan is null, so the planner sees nothing, it only sees vehicle and obstacle, so it will need to make a plan. At some other general framework, let's say there was some infeasibility due to this vehicle, it could not decide whether to go right or left, so it was ending up with plan right here. Because this vehicle moved, it changed its speed, now I can extend the plan, and if there are some obstacle I can decide how to go around with them. Or as in this scenario, if I cut my plan like this over here, now there might be a new way that I can extend my plan. So either because my initial plan was null, or because my trajectory was previously ending up in some infeasible region which is now feasible, or because I cut my plan and there are new ways in which I can extend my plan, I'll always extend my plan, which is what I would be presenting ahead in how the plan can be extended, which will be the main part of this presentation. And then as in every such kind of planners which optimize as the vehicle moves, initially how my plan would have been, it would have been going quite close to the obstacle like this. Now we would like to push it up a little down, so that this is the feasible plan. This is clearly bad, I want to travel like this. So I would be optimizing my plan. I'll be basically locally optimizing my plan, and that's what we've seen, that every such kind of planner which plan as the vehicle move, they keep on optimizing the plan as the scenario changes, or the initial plan generated was not quite optimal. As the vehicle moves on, they get in time, and they try to use that time in optimizing the plan. So that's the second thing that I would be doing. For optimizing the plan, of course, I'll be using the principle of elastic strip. And for plan extending, I'll be using in the concept of lateral potentials, as we'll see. So this part of the problem is already solved. We've seen in lateral potential how the forward distances could be used to convert distance into speed, and then I'll be setting the same speed. I've already told the what is the infeasibility criterion, so this part of the problem has been solved. I'll basically iterate my trajectory. I'll see the first point which is infeasible, I'll cut it. So I need to solve these two problems, which are the main agenda for the rest of the presentation. And whatever I had been very untidily drawing this a neat drawing of it, at every time the plan is basically seeing the plan. Whenever it sees the plan, it trims it computes the maximum speed as per the new speed, it extends it, and it optimizes the plan. And this variable is always maintained by my planner, and anytime the controller needs to move in the vehicle, this is what it sees. It's the currently best plan, because of which again the map changes, or their vision algorithm, because of which map changes. So this is the loop which will happening continuously, and we need to see two things, that is how do we optimize the plan, which was my problem 2, and how do we extend the plan, which was my problem 1. And what I haven't told so far, I'll take it now. The top part of that figure, I need to be, as I said, very wary of scenarios like this where there's an obstacle out here and I come very close to it, because of which I always said that I will be maintaining in a trajectory known as tau obs, known as my obstacle only trajectory, which is computed only considering the moving vehicles and nothing else. So that is one thing that I will always be considering and maintaining. Now I need to only consider this trajectory for scenarios like this, where this is what my normal trajectory looks like. If my normal trajectory is ending in an obstacle, then it's likely to be such a scenario. And if my normal trajectory is not ending up in an obstacle, but rather it's ending up in some vehicle out here, then I know that worst that I can do is that I'll use this trajectory, I'll come up to this point and I'll simply start following this vehicle. If it turns right, I'll also turn right. If it turns left, I'll also turn left. Or if I have got a better plan. So this is clearly not this scenario that I'm very scared of. Scenarios like this, where my normal trajectory ends at a vehicle in place of an obstacle, or it ends at a road end in place of an obstacle, they are safe. I need not be scared of this thing happening when I'm doing such kind of things. Unless and until there was an obstacle out here in which both this vehicle and this vehicle would be trapped in such a situation, in which case of course this vehicle would be to be blamed. The vehicle that I'm planning was simply following this vehicle. It's all the fault of this vehicle. So overall, this is the scenario that I'm very scared of. This is the scenario that I need to avoid. This is the scenario that I need to get rid of. And therefore, I sense any scenario like this where my normal trajectory is ending in an obstacle. If it's ending in an obstacle, I will say that I'm in a fail-safe mode, I'm in a recovery mode, I'm in a fallback mode. Else, I'll drive normally. And if I am in such kind of recovery mode where I have sensed that something like this might happen, I never speed up. I basically never at all speed up. And what I do is that I make sure that I do not go so close to the obstacle, but rather I keep a comfortable distance from the obstacle, a minimum of d0 or do. So I have sensed this kind of scenario which I was very scared of, and I have said that when I have sensed it, I will make sure I do not go at a distance more than do from the obstacle. I'll brake myself well enough so that I stop before a distance of do, and Even this is a scary scenario where I am static obstacle is here and I am at the distance of DO, but at least now I can wait for the other vehicles to go, wait for the road. Suppose there was two vehicles here, I can wait for both of them to go. I can wait for the road to clear, and when both these vehicles are gone, they are somewhere here, I can nicely steer myself here. So that is what I basically do. I sense this scenario, and whenever I found it, I stop at a distance of the O. And that's a graphical presentation of what I just draw. I'm trying to plan stop at a distance of the O. This is my obstacle only trajectory. When this trajectory was made, the blue vehicle was not even considered. So that's why it's obvious that if it follows this trajectory, it will collide. And this is my normal trajectory that's ending up an obstacle. The only point is I measure the deviation between these two trajectories right at the end. If the deviation is very large, then my DO will be very large, and if deviation is very small, my DO will be very small. So let me take in three cases. This was my normal trajectory ending up at the obstacle. This was my trajectory DO. Now the deviation is very small, and it's obvious that this vehicle waiting out here, only slight part of it is ahead of the obstacle. So even if I'm close to the obstacle, it does not matter. The other case is, suppose this is my normal trajectory and this is my obstacle avoidance trajectory. The distance is very large, which means my vehicle is waiting out here. Now I have a long distance to cover. In fact, I have so much amount of distance to cover. I'll need to steepen very sharp, and because I need to steepen very sharp to overcome whole of the obstacle, here I only had to overcome part of it. Here I only had to overcome half of it. Now I have to overcome whole of it. So I require much larger distance. And that would be plan extend, and with this I come to the first problem that I said that we would be solving with all these principles that we have studied. The first problem was the plan extension, and the plan extension is rather simple. I have my vehicle out here, there are some other vehicles and obstacles out here. It basically uses the general lateral potential method to say how should I move, and my lateral potential measures again sees distance from the front, it's from the diagonal, from the side, from the back, and it says that you should, in this case there's an obstacle, there's a vehicle right in the center, so I can do two things. I can avoid it at left, in which case my new scenario would be here, or I can do turn right, in which case my new scenario would be here. This is how the two scenarios would be. Now remember, in lateral potential the vehicle was actually moving, while in elastic strip or in this algorithm the vehicle is not actually moving, it's only going on in the head. It only says if I do, then what will happen. It's a kind of graph plan situation that's only going inside the vehicle's head out here. And of course I can decide my new position. Static obstacle, the position will not change. I use some uncertainty model to say that by the time I move here, how much this vehicle would have moved. So I move this vehicle by the uncertainty model, and like this, now that I have decided, I can use the lateral potential again and again. My final trajectory would be like this for this scenario, because there's no other new vehicle combined. So there are no options of strategy parameters here. My trajectory would be like this until I find a static obstacle, in which case again there are two options. I turn right or left. I compute both these possibilities here. In one case I will have this as the trajectory, and in the other case I will have this as the trajectory, and clearly it can be seen this trajectory is the best. It's longitudinally the most ahead. So out of all these three possibilities, this is what my final trajectory would come out to be. In practice, it's very simple to understand this. You need not go into that amount of detail. There were a couple of obstacles. They were some other vehicles, I simply call lateral potentials for all combinations of obstacle avoidance and vehicle avoidance strategies. So I simply said one strategy, turn this left, failed. Turn this towards the right, turn this towards the right. This is what happens. Turn this towards the left, turn this towards the right, turn this towards the left, and these are all the combinations possible. That's what I've done out in this graph. And the only thing is my lateral potential was working with both speed and trajectory. Now speed is fixed, so while calling the lateral potential, I will not change the speed. I'll use a continuous speed. And the second thing is that whenever I work with such kind of methods where inside my head I'm moving the vehicle on some trajectory only inside my head, granularity is a principle that only comes in. So suppose out in the same scenario, I can see that the vehicle and the obstacle are far ahead, so I can move them with the same speed. I can make them jump by some large amounts. Now the vehicle is near, so I'll have to make the vehicle jump or change its steering by smaller amounts. So that's what I would be doing. Here, large amount, far off, again, far off, obstacle, large amount, obstacle near, then small amount. Suppose I'm turning right, then smaller amount and smaller amount. So even though the speed is same, my jumping speed or my granularity, it's changing. This is an extreme case, of course. I was taking much smaller cases here. I have a much smaller cases throughout. So I have used in some kind of granularity control, and the speed indicator of lateral potential is my indicator of granularity control. That's obvious, and that is what summarizes the entire extension algorithm. Simply compute by all strategy and take in the best strategy that you have encountered. Now the only problem, of course, a problem that I have been discussing since the very beginning are these scenarios where I'm very scared of my trajectory ending in a static obstacle. So suppose this was a static obstacle, I was here, there was some other vehicle here. In this, what happens? These were the scenarios that I was very scared of. So if this happens, if the final trajectory that I selected that ends with a static obstacle, I again calculate my tau obs. So I simply delete this vehicle, calculate a new trajectory. The only problem that will come is that I'll draw a magnified view of this. This was the obstacle. My tau was trying to drive the obstacle towards the right of the obstacle, and it could not because his space was less. And my tau obs is trying to drive right of the obstacle. So my trajectory is taking me towards the left of the obstacle, and my tau obs, which is the obstacle only trajectory, is trying to take me towards the right of the obstacle, which is a natural ambiguity in the two strategies. So I simply undo the ambiguity. I simply say that my tau will have all the strategy parameters as dictated by the tau obs. So that means if my tau obs says right of the obstacle, I'll recalculate tau such that it goes right of the obstacle. So there's a little bit of ambiguity that was involved that I have, by a very little tweak, I have undo, and that's a better diagram of what I have been talking about, calculating all the possible ways that in which every possible obstacle right or left can be avoided, and this is what comes as my optimal trajectory as per the settings that I've just told. So that was problem 1 in my general algorithm framework, which had to do with the problem of plan extension. So this was problem 1. I'll now be considering the last and the only problem, which is the problem of plan optimization. And the problem of plan optimization, because we understand the general concept of elastic strip well nicely. I know if there are obstacles out here, this is my trajectory. Each one of these obstacles repels this trajectory. The road boundaries repel this trajectory. They'll not let it come inside. This obstacle repel this trajectory. This repels this trajectory. So there are a lot of repulsion forces that this trajectory is encountering. Along with that, for the purpose of this, I construct some crosses out here where all the computation will take place. The computation will only take place at these crosses. My source is fixed, I can do nothing. My goal is fixed, or the last point is fixed, I can do nothing. I take in any general point out here. Let me take this general point out here. It's repelled by the force from this obstacle right here. It's repelled by force from this obstacle right here. It's repelled from this boundary force out here. But it is attracted by this point and it is attracted by this point. So if I draw a magnified view of these three crosses, these 3 points need to, the internal spring force, it's trying to straighten up this alignment. They are trying to attract each other, and it's only the force that's not that's allowing them to do. And therefore my final trajectory, which looks so crooked like this, will finally get only by the application of these forces to be that smooth. It's a general property of the elastic strip. There's nothing that I'm externally doing. The only problem with optimization with elastic strip is that if I let my points be very general, let them move by all these forces, then sometimes they become very close to each other. This point can move here and this point can move here. So in order to stop them, I have basically tied each of these points to clamps. I basically tied each of these points to such rods. Any such point can only move in this rod. So if you, I'll again draw a magnified view of this. If you apply in force here, if you apply in force here, and if you apply in force here, ideally it should move somewhere in this direction. But now only its component in this clamp would be taken and it will move a little top. Its motion has been restricted. So that's the basic principle of elastic strip that I have used. There is again a scenario that we have been discussing so far, which again plays a role in this. It plays a role at every stage. It plays a role here also. If there's an obstacle, my normal trajectory ends with this obstacle. Now, a central question which I have delayed it for so long is, I have a tau obs. Do I follow tau obs, or do I follow this trajectory out here? I follow my normal trajectory out here. The problem is, if I follow my normal trajectory out here, I come here, I get at rest at a distance of dO. I simply stand still and I wait for vehicles to clear, things to improve. I keep waiting, and when everything improves, I go like this. And if I follow tau obs, then I go here, I wait for vehicles to clear, I wait for vehicles to clear. After blue vehicles goes, I come here, but then again there's another vehicle which says I will also go, so I will wait for that vehicle. While my obstacle is far off, this is too large. So in general, I had an obstacle here, my tau said turn very late, my tau obs said turn very soon. What do? And obviously what I do is, I follow neither tau obs. I say let me do something in between. I'll say I'll follow tau, but I'll make my tau look more like tau obs. And hence this concept of drift comes in. I'm applying a force at every x, at every of those points out here. And these points are taking me towards tau obs. So I'm applying a drifting force here. What this drifting force will do is that it will make tau more like tau obs. And as a result, the final tau that I'll get, that will be not tau, it will be not tau obs, it will be something in between. And that's what I said, that I'll neither turn too late, I'll neither turn too early, I'll turn somewhere in the middle as a result of this drifting force. So these are all the forces enlisted in one slide. I of course had the internal spring force where the points were trying to attract each other to make them as a single line, as a single string. There was lateral force, which was repulsion from the road boundaries and the obstacles, and there was a drift force where tau got converted more or less into tau obs. And we know it's a cooperative system, so in a scenario like this where a vehicle comes here, it plans its trajectory, and afterwards the other vehicle comes here. Now there's why my plan extension takes into account cooperation. So but the planning till this level has already been done, so it's only further that it can drift left or right. It's not any before that. Or I can cancel my entire tau and make a new plan for this, in which case it will be cooperative, which is a waste of resources. Such a big plan calculated, we cannot throw it away. So I said that I add cooperation externally, where in such kind of scenario, when it is apparent whether overtaking has to take place on the right or the left, where clearly this vehicle is more on the right, I'll initial parts of the trajectory, I'll drift them more towards the left. So that's how cooperation has been artificially added, and these are all the forces in a good diagram, in a good version of the same diagram that I draw. Why I specifically want to highlight on this slide is, suppose I'm considering this X out here. Now by the time this vehicle reaches here, this vehicle is not here, this vehicle is not here, this vehicle has moved in a point here, which is of course by some uncertainty model. There we consider uncertainty in position and speed to get in this position. As this vehicle moves from here, suppose it was a fast moving vehicle and this was a very slow moving vehicle, it adds here. So this point is not under repulsion by this vehicle, it is under repulsion by this vehicle. And similarly, this point is under repulsion by this vehicle, which is what we expect the position would be when the vehicle reaches out to this point. So in the previous slide, I informally said that all the vehicles repel. The vehicles do not repel. The prospective new positions of the vehicles, they repel. And this is a more fundamental diagram. This was the initial plan, and this was a plan after optimization. Of course, here the initial plan looks as good as the optimal. So I said that let me make optimization so that my algorithm is very conscious of clearance. It just wants maximum separation. It wants a very large maximum separation. So therefore, when the vehicle was here, this road boundary exerted a very big force to it. It exerted a very big force, and quickly it drives at the center. And after that, it's basically always at the center, maximizing clearance, because the forces are very broad. They are very large, so it's always at the center. Of course, this was only used for analysis point of view. The actual trajectory followed would be this, wherein we won't make one of the forces excessively large. And finally, these are the results. This is the multi-obstacle avoidance scenario. This is the scenario that we have been very scared of. Now look at it. This firstly, it did not go very near, and secondly, it waited for both these vehicles to clear, and nicely following something between tau and tau obs, it cleared while a new vehicle was behind. This is the double overtake. And this is again a double overtake, except for there are too many vehicles. There are 6 vehicles as I can see. They all go smooth. And this is some analysis that I'll briefly say, only say what am I actually doing along with it. There are 2 strategies. One says that only for optimization, only and only maximize clearance, and that's what the slide I previously said. If I make the spring, this force too large, then it will quickly get towards the center. It will travel straight. It will travel at the center of the obstacle and the road boundary, and so on. So a very high path length. It's clearly traveling unnecessary distance out here. Very large path length and very high clearance, a very high average clearance. The distances are always large. While if my spring force was very short, I would have taken this route. Small clearance here, but a small path length as well. And similarly is the internal force. If I make my elastic strip very elastic, now I've got confused whether high elasticity means it will quickly converge to this, or high elasticity means it will slowly converge to this. So if my spring is very stiff, it quickly converges. If I have got a very stiff spring, then what will happen is this point will attract these points very badly, much more than what this obstacle can repel. So it will be nearly kissing the boundary, very small clearance, very small path length. And the converse, if I let my spring be as loose as possible without applying any force, these will not attract, while a very small force from the obstacle can repel. So that's broadly what these two fancy diagrams mean out here. And that would be all for the presentation. Thank you.